Okay, so hello to everyone. Today, I'm glad to welcome a very known expert in this field, of quantum optics. Okay, I would say that since he is invited by Andrei Semyonov, we will give him this possibility to introduce the speaker. I just wanted to say to remind that. Our general rules for this seminar, of course, speaker choose his own format, but I just wanted to say that we usually do not limit people with questions. We even encourage the people to ask questions and during the talk and after the talk, and we also do not limit the speaker with time. Usually it takes more than an hour, but this is, of course, up to the speaker to do it. So I welcome Alexander here, and I give the floor to Andrei Semyonov to introduce the speaker. Please, Andrei.
Oh, thank you very much, Alexander, for giving me a possibility to present our guest today. So, ladies and gentlemen, today we have a special guest, Professor Alexander Lvovsky from the University of Oxford, United Kingdom. Professor Lvovsky is for sure one of the top list of experimentalists working in the field of quantum optics, with its application to modern quantum technologies. His expertise covers mainly the field of generation and characterization of non-classical states of fields. Particularly, his very interesting last work was related to Schrödinger cat states. So Alexander is one of the persons who was able to raised Schrödinger cats from Schrödinger kittens, Schrödinger cats from Schrödinger kittens. Yeah. And to introduce our guest, I just remind some points from his bio. So Alexander Lvovsky has graduated from the Moscow Institute of Physics and Technology in 1993. And from 1993, he is a PhD student at the Columbia University in the New York City, supervised by Dr. Hartman. Starting from 1998, Alexander Lvovsky was working as a postdoc at the University of California in Berkeley and the Universität Konstanz in Germany. And starting from 2004, he's professor at the University of Calgary in Canada. Starting from 2008, he is full professor at the University of Oxford in the United Kingdom. So today we will have a really nice, I believe, nice talk with nice and very modern physics, which join not only fundamental things, but also its application. And this will be about optics and neural networks which working together. So please, Alexander, feel free. Time is yours.
All right, thank you. So yeah, that's the title of the talk. That's the group, and yes, so there is a university group, which is, well, over the course of time we've done quite diverse line of research. We used to be a hardcore quantum optics group, but then we diversified quite a bit, mainly towards machine learning and optical neural networks. So we've done all sorts of stuff that's related to quantum optics, machine learning, and even robotics. So the talk today will consist of 3 parts, as you've seen in the abstract, and they're largely unrelated to each other. So if you get distracted during one of the parts and did not understand it, don't despair. Then you can check back in during the next part. So the first part is actually most difficult. It's about neural networks. And well, I guess I should start by stating that machine learning is taking over the world. This statement is now more obvious than it was, say, 5 years ago. We are all experiencing it in our everyday life. And I like to make this controversial statement that machines now perform better than humans in those worlds they have an opportunity to know about. Yes, so they can play chess better than humans, they can recognize faces, they can calculate integrals. So if they have complete knowledge of the environment, then can actually do better than humans. The only environment in which they have not yet surpassed humans is our everyday world, right? And that's why, contrary to our expectations of the future, intelligent machines are not doing physical work for us. They are now doing intelligent work for us, leaving the physical work to humans. Anyway, machine learning is powered by neural networks, and I don't know how much you guys know about neural networks, so I'll give you a very short tutorial into what a neural network is. So suppose we want a machine to perform some task, for example, distinguish a cat from a dog. Yeah, you get some bitmap, and you want to tell whether it's a cat or a dog. Now, mathematically, this is a function, right? The input is a vector. The bitmap, it's a square bitmap, but still a vector. And mathematically, it's a function that produces two numbers. Given this input, produces two numbers, the probability of it being a cat and being a dog. Yeah, and apparently our brain is quite good at calculating this function. So the question is how to get the machine to calculate it. And the answer is that the general form of this function implemented by the machine is as follows. You take the input vector, you multiply it by some matrix, called weight matrix, and we are free to choose this matrix. And then we get the vector at the output. Then we apply a so-called activation function, some kind of nonlinear function to each element of the output vector. This one we do not vary. It can be essentially any activation function, for example, hyperbolic tangent. And we repeat this many times. Yeah, one layer, second layer, third layer, then some kind of summation, and that gives us the output. And that's called artificial neural network. And there is a mathematical theorem which says that basically any function f can be well approximated given such a structure, provided that there is enough layers and the dimension of each layer is sufficiently high, you can get good enough approximation. Of course, you have to pick the weight matrices correctly, and that's what consists. That's what is training of the neural network, and that we'll discuss later. Now, as I said, artificial intelligence neural networks seem to be taking over the world, but actually there is a caveat. The caveat is that current digital electronics is actually significantly slower. Well, in terms of speed, it's gradually catching up, but really significantly less efficient than, for example, the brain, right? You can see 3 orders of magnitude. So at the moment, already 2% of the world's electric energy is consumed by data centers. And this number is growing exponentially. In some countries, say in Ireland, it's actually more like 7%, the last number I've heard. So it's really, we're afraid of artificial intelligence, but one must understand that we are, if we are not changing the technology, we're actually going to soon hit a brick wall. Now, what is the reason? Why is the electronics so much slower? The answer is, well, because it's digital. Because look, the most computationally bulky part of a neural network is actually this vector matrix multiplication. Now, even if we multiply 2 numbers, 2 32-bit numbers, it's like 1,000 single-bit multiplications. And, within the neural network, we have billions and trillions of such multiplications. Obviously, it's going to be slow, it's going to be inefficient. In a brain, in contrast, the entire vector is collected via dendrites, is transmitted to the body of the neuron, where the weight matrix is contained, and multiplication takes place, and then if the result is above a certain threshold, then activation occurs, nonlinear activation occurs, and the activation spike is transmitted via the axon. So the whole vector matrix multiplication is analog, right? It's a single physical process, and that's why it's so much more efficient. And then the question arises, can we come up with a technologically accessible platform that can perform like this, like the brain, and not like this? And the answer, if we ask ourselves this question, is optics. Because interference and diffraction of light during propagation actually realizes exactly that matrix vector multiplication, as you'll see in a moment. So that's why this technology has been developing rapidly, mostly in laboratories, but it's starting to get commercialized. So our startup Lumai is all about that. There are two main venues in which this can be realized, either free space or integrated. So free space is not on the optical table, right? You encode information in the spatial structure of the light beam, and then use spatial light modulators to express the weight matrix. Or alternatively, you can have an integrated implementation in which the information is contained in the waveguides and use integrated beam splitters for matrix vector multiplication. The advantages and disadvantages are clear. I mean, the disadvantage of this is obvious from the picture, right? You cannot make it at the factory. You need to align it for hours and hours. We'll get to that. But the disadvantage of this is that the technology is not there yet. With this, we can get dimensions of hundreds and even thousands. With this, we can barely get a dimension of 10, maybe 20. So that's a problem, right? That's why, I would say this is today, this is tomorrow, and we are working on this. Now, I mentioned some numbers here, 10 power 16 operations per second and 10 power 17 operations per joule. I want to explain where this number comes from. Suppose you have matrix vector multiplication 1,000 by 1,000, right? That means 1,000,000 operations, right? So you input your vector, you have you have 1,000 vector elements, right? And you introduce them into your network using electro-optical modulators. A typical electro-optical modulator bandwidth is like a gigahertz, 10 gigahertz, maybe on 50 gigahertz, right? So you multiply this number by this number, you get 10 power 16. In terms of energy efficiency, it's also kind of quite clear. What you want is that you need a reasonable number of photons in each of the outputs, right? In principle, if you have few outputs, you can even do with less than 1 photon per operation, right? If you have like 1,000 outputs, but 1,000,000 operations, then you can have less than 1 photon per operation, which is quite remarkable. There was a paper on this. But if you have, say, 10 power 4 photons in each output, right, which is quite reasonable, then it's 10 power 7 photons per multiplication and 10 photons per operation. If you divide by 1,000, get 10 photons per operation, 10 power minus 17 of a joule. So that's
Alex,
yes, please.
Just short question, but this is just for very some ideal case and without somehow losses of the signal should be
absolutely. Yeah, that's the number we're aiming for. That's the number we showed.
Intensity, yeah. How intensity affects this? So it is estimate. There is no intensity, for example, in this estimate or.
Well, no, there is, because 10 photons is 10 power minus energy is relevant, not intensity. So 10 photons is like 10 power minus 17, 10 power minus 18 of a joule. So of course it's ideal, right? Of course, to operate the laser, we have a huge overhead. We have to operate the modulator, we have overhead and so on. So these are all significant issues, but
these are the limits which could be reached in principle.
Yes. In principle, theoretically, yes. Right. Yeah. So for comparison, this is the newest GeForce NVIDIA, and you see it has 10 power 14 operations per second, but 10 power 11 operations per joule. Now, how to do it physically? How to multiply a vector by a matrix? Well, this is a bit simplified, but it's good for explanation. So you have a vector, which is like, a mosaic, right? So some spots are brighter than others. Then what you do is you expand your vector physically, you fan it out to the matrix, like this. You fan it out to the matrix, so each row of the matrix gets one vector element, right? And then you converge, right? And then what you do is you multiply, right, to the matrix. Each matrix element is then gets pairwise multiplied by a vector element. And then what you need to do is a summation, right? How do you do the summation? You apply a lens
which converges the vertical dimension, which was previously collimated, and collimates the horizontal dimension, which was previously diverging. Yeah, and then you put in a slit which selects only the 0th spatial component of the beam. And that corresponds to summation. Remember, in the Fourier transformation, you take the 0th frequency component that corresponds to integration. That's exactly what's done here. That's the experiment. So we use a liquid crystal SLM with our weight matrix, another spatial light modulator called the digital micromirror device to produce a vector. And this slide, next slide takes some time to load. Here it is. And well, here's what the vector looks like. The first column is a vector. The second column is the matrix. Here you can see the third column, you can see element-wise product of the vector of a matrix, and then you you do the Fourier transform and select a component like this. And well, here it shows the dimension of 56, but in fact we can do up to 1 or 200, right? And the error corresponds to about the precision that we get is about, well, we say it's 8-bit. The referee said it's about 5-bit. So we have to find a compromise. But anyway, so that's where we are. We can also do it with complex numbers. Then the big question is how to train a neural network and how to do it optically, right? So as I said, this whole thing works only if the neural network is trained. That is, only if this weight matrix implements the function that we desire. How do we train a neural network? First, mathematically. Mathematically, to train a neural network, you need a so-called training set, which consists of multiple examples of the input vector. Oh, there's a typo here, should be X. So multiple examples of the input vector and correct answers, right? And then you send all these input vectors into a network. That gives you some output f of x. And then you calculate the so-called cost function, that is the mean squared error between the neural network output and the correct answer, right? The important thing about this cost function is that it's differentiable with respect to the weight matrix. That is, you can calculate the gradient of the loss function with respect to the weight matrix and therefore perform gradient descent, right? You can then apply small changes to the elements of the weight matrix so that the loss is minimized. And that's how basically the training occurs. Now let me go a little bit more into mathematics. That's kind of the only there will be more equations in the talk, but this one is kind of an important one. So again, we want the gradient.
Just one more short question. Very general, of course. It is clear that you can go this way, but it is not. You need the absolute maximum, but could be a many of local maxima. And
it's a huge problem. There's a whole bunch of people working on this. I think now they kind of know how to resolve it. Apparently in a sufficiently large neural network, it's not that big of a problem. But yes, that's that's a whole field how to avoid local minima. But let's not talk about this for now. Let's look at this expression for the gradient. Now the gradient is a matrix. And the matrix is an outer product of two vectors. One vector is the neuron activation value, so the actual value of the vector carried by the neural network. But the other vector is so-called error. Let me tell you what it is. What is this delta? So delta has to be calculated backwards by propagating through the network backwards. For the last layer, it's just the difference between the network output and the correct answer. That's for the Lth layer. What you have to do to calculate the error for the previous layer is you multiply each of these each value of the error by the derivative of the activation function, and then multiply by the adjoint of the weight matrix, and that gives you the error in the previous layer. And then you can go back again and eventually calculate the error vector for all layers. This is the so-called backpropagation algorithm proposed by Jeff Hinton, and that's basically what created the field of machine learning the way we know it today. It's a very fundamental paper. Now, let's now ask ourselves a question: how can we do the whole thing? How can we implement the whole thing in an optical neural network? Well, the way it's usually done, if you look at a typical optical neural network paper in literature, what you will see is that people will just model an optical neural network in a computer and then train it digitally. So train the weight matrix digitally and then program their spatial light modulator according to what they've trained. And obviously there are two problems with it. A, it's slow. Obviously, we promised that optical neural networks are slow, are much faster. So if they're still trained by means of a digital neural network, what good is this? And second, there are errors. That is, if the SLM does not perfectly represent, if there are some errors, some dust, some aberrations, and so on in our SLM that are not perfectly represented by our model, then obviously this neural network will not work very well. So a partial solution would be to calculate. Well, we have the forward propagation in an optical neural network, so we can actually calculate this vector A, the neural activations, optically by forward propagation, right? But calculate the errors via the digital model, right? And that solves a part of the problem. That addresses this problem, that kind of reduces the sensitivity to errors and noise. Of course, it's still slow because the digital computer is still involved. But it kind of works as is shown. Well, in this slide, what you can do is you can compare the dashed curve and the solid curve. So a dashed curve is a fully digital neural network, so no optics at all. And in the solid curve is an optical hybrid network, that is the error calculated digitally, but the activations are calculated optically by forward propagation, and you can see that the performance is quite comparable. And in this slide, you can see the effect of noise and errors. So here, for each condition, you see three columns. The yellow column is all digital. So the perfect case, everything is calculated mathematically. The red column is in silico. That is, we model our neural network via a computer and train it via a digital computer. And blue column is our hybrid scheme. And well, what you see here is that when we introduce various kinds of noise, then the performance of a neural network trained in silico degrades, whereas the performance of a neural network trained in our hybrid style does not. So that's a nice result, but of course, the big question is, can we also backpropagate optically? So can we also calculate the errors optically? Can we calculate optically the entire gradient? And the answer is, part of the answer again is look at the forward propagation, look at the backward propagation, right? So here we multiply by the weight matrix, apply the activation function. Here we first multiply by the derivative of the activation function, and then multiply by the adjoint of the weight matrix. It looks quite similar. And in fact, one immediately thinks of, what if we propagate our light just simply backward through the same network? Yeah. And the good news is that the linear part of the operation does give us the correct result. So if we propagate backwards, it actually corresponds to multiplication by the adjoint matrix. So that's good news. The bad news is with the activation function, because you see when we propagate forwards, we apply a nonlinear activation function. When we propagate backwards, however, we have to multiply by the derivative of the activation function, so something entirely different. And the question is, That's a problem, right? Because there are not many optical systems, optical media that behave differently for forward and backward propagation, right? And in addition to like for backward propagation, it must be not something arbitrary, not an arbitrary linear behavior, must be multiplication by the derivative of the activation function. So here's the solution. The solution is that you have to use a special kind of nonlinearity for which all three criteria fortunately work. And the type of nonlinearity that we found to work is Sacharov absorption, right? I remind you what Sacharov absorber is. It's like a two-level system. When you apply, when you propagate light through it, then of course atoms are sitting at the bottom level, so they'll absorb. But if the light is very strong, if the field is very strong, then there'll be an equal number of atoms at the top and at the bottom, and then you have as much absorption as stimulated emission, and then the absorption will be greatly reduced. So that's what Sacharov absorption is. And then another idea would be to make the forward signal strong, so you have nonlinearity, and backward signal weak. For weak signal, of course, no nonlinearity is present. And then, well, very fortunately, it turns out that for Sacharov absorption, for the specific case of Sacharov absorption, we also have the third condition satisfied. That is, we approximately multiply by the derivative of the activation function. I will skip the slide. So instead, I'll just show you what the setup looks like. Right, so this is our matrix vector multiplier. This is our nonlinear activation, the Sacharov absorber, which in our case is simply rubidium vapor cell. So yes, so we multiply a vector by the matrix, we apply activation, and then from the backward direction, we propagate the error, right? First through the activation function, then through the same vector matrix multiplier. We split off an error here by the beam splitter, and we split off the activation. We split off the activation value here by means of another beam splitter. So we get our two vectors. We can multiply them either digitally or electronically, and we get our gradient. The last remaining question is question.
This absorber is a single body or is divided by channels?
It's a bulky rubidium cell, right? So when you send several light beams through it, each of them interacts with rubidium on its own. There is some crosstalk, so we had to take some effort to get rid of the crosstalk, but we were able to.
Okay.
Yeah. So how to calculate the error at the last layer, right? So I remind you that the error at the last layer is simply the difference between the activation function. Between the neural network output and the correct answer. And the answer is this can also be done optically by means of destructive interference, right? So you take your neural network output and then you send the correct answer via laser, you overlap the two on the beam splitter, and that gives you the error value that you can propagate through the network. And well, so here's the experimental result. So here you can see the first vector matrix multiplier, rubidium cell for activation, second vector matrix multiplier, and the output, right? So then this is the error in the second layer, just directly calculated at the output. This is the activation of the first layer. The error of the first layer has to be split off after the back propagation through the activation, and the activation in the 0th layer is simply the input vector. And well, here you can see in this slide the activation function, and in this slide you can see the behavior of the behavior of back propagation. You can see that it follows the theoretical expectation. And well, here you can see the performance of the trained neural network. So the task that we pose to our neural network is quite simple. We ask it to distinguish between two classes of objects whose two-dimensional coordinates are given, right? So the first class is located, well, here in the center, and the second class is located in the periphery. And those examples that you see are elements of the training set, right? So that would propagate first forward and then backward. And the picture and then the background here, blue and beige, is the actual performance of the neural network. And you see that it performs well. It classifies the two classes of objects correctly. And the performance is significantly better than if you do hybrid training, right? And if you use optical inference, but in silico error backpropagation. So yes, so that concludes the first part of the talk. I will maybe stop here for a couple of questions, if there are any.
Please ask questions at this point. I just, when you're thinking about question, I just wanted to ask more maybe about material, how it is made. I mean, physically, this weight matrix.
It's simply a spatial light modulator.
And
it's
this.
It's a liquid crystal display.
Its properties depend. It is not my field, just optics, but therefore I'm asking your stupid questions. But I mean, how it is transparency depends on intensity, or
no, it's a liquid crystal display, right? No, transparency depends on the voltage you apply.
Voltage, okay. And you adjust this voltage on this, change this voltage on this back process, right?
Well, if you train it digitally, then the digital training tell you which voltages to apply to each pixel.
But when you do it optically, I did not.
When you do it optically, yes, you calculate the gradient and you gradually change the voltages according to what your optical neural network tells you.
According to these detectors, which you have shown, which show you on this image, just on your picture, from where you take a signal to correct this transparency, let's say.
That's right. So the signal is the outer product of two vectors, right? So for example, this error and this activation function, this error here and this activation function here.
So you calculate it electronically and adjust the voltages accordingly. Yeah?
The outer product is calculated electronically. So the actual vectors are calculated optically. The outer product is calculated electronically, but it can also be done optically. We just don't do it.
And how much is can you adjust? I mean, it is somehow gradation of intensity. Yeah, how it is defined.
I'm not sure what you mean.
You have some range, some range of intensities. You change voltage, but your transparency it is proportional to voltage, or how it is?
Yes, kind of. I mean, of course, it's not perfect, so we have to calibrate everything carefully. But yes, in the zeros approximation, that's what it is.
And what is this range of orders of possibility from? How many values you could get in one cell?
Well, I mean, the pixel resolution is thousands, right? It's like 1,000 by 1,000. But each particular pixel is 8-bit.
8-bit, it's enough. Yeah, okay,
that's right. But actually, it's more complicated because we don't use the spatial light modulator as an element of variable transparency. We use diffraction, but it's beyond the. It does not. We can discuss it offline later.
Okay, thank you.
May I ask a question also, Alex?
Please.
Alex, sorry, about your special modulator. It seems that I'm not really an expert in the field, but it seems that liquid crystals are characterized by large absorption, and they also nonlinear, it seems, elements. So this is absorption and nonlinearity. Does it affect on your result?
Well, it introduces losses, especially since, as I said, we use diffraction. So we don't look at the transmission. We look actually in the first order of diffraction for technical reasons. Okay. So losses are significant. This is just a proof of concept experiment. This is not faster. This is not less. This is not more energy efficiency. It just shows that, in principle, one can train a neural network optically.
And what about nonlinearity?
Negligible.
Okay, thank you.
At these intensities, it's negligible.
Okay, thank you very much. So
All
maybe
right.
we have other questions I should ask.
This is
Yeah,
Mike.
please.
Yeah, Mike. Just do I understand that graphene structure, as you described, is a substitute for the vapor chamber where you actually were performing this function?
You're referring to this slide, right?
Yes, the free space.
Yeah,
free space
so
vapor cell.
Basically, we have no idea about graphene, but there are papers that demonstrate such absorption in graphene at very low intensities. And therefore, we believe that in an integrated implementation of a neural network, graphene could play a role as the activation function.
Okay, so that would mean some type of heterostructure that would need to be constructed on silicon nitride. Is that what you're proposing as a platform?
We are not proposing a specific platform. Could also be lithium niobate, could be silicon nitride. There's different people, actually people try both of these. People also try silicon, regular silicon. So, there is no consensus in the community which platform is better.
Understood. Thank you for answering the question.
Welcome. All right, I'll proceed to the second part, and the second part is more entertaining. It's about using a robot to align an optical setup. Now, I understand that not all of you are optical physicists, but those of you who are, well, this is a picture from the Max Planck Institute. Not all optical setups look like this, but basically each of these mirrors has to be aligned to like a micron, right, for the system to work properly. And that's what experimentalists do, right? They spend hours and hours aligning their optics, and then something goes wrong. They get another idea, and they have to realign from the beginning. The question is, can we assign this to a robot? And well, the answer is, oh yeah. So that's what we discuss. So the most sort of common type of alignment procedure is mode matching. That is, if you have like a Mach-Zander interferometer, you split the beam, right? And then you want two beams to overlap, and you want them to overlap precisely in like position, direction, beam, and divergence. And then you get good interference at the output, right? So if you change the path length difference, the visibility, if it's well aligned, the visibility is close to 1. If otherwise, it's close to 0. Yeah, and here it kind of explains why the visibility is close to 0. So if you have two beams that are not perfectly aligned, then you see you have the spot corresponding to the first beam, to the second beam, and you have some fringes between them. So if you have bad alignment and start to change the path length, it will look, the interference picture will look somehow like this. If you have very good alignment, on the other hand, right, and change the path length, then the two beams perfectly overlap, so you just have blinking, visibility equal to 1. So you want this and not this. And here's how a robot can do it. Well, here's our setup, and again, it's just a Mach-Zander interferometer. We look at the interference pattern with the camera, right? Take the video data to our reinforcement learning agent, who then sends commands to motorized mirrors and lenses to change the beam. Now there is a piezo element here, which changes the path length difference, and it does it in a sawtooth fashion like this. Right, now, if you know about reinforcement learning, standard formalism, right, we have some kind of environment on which our agent can perform actions, and in response to the environment, well, it's to change its state. It will provide the agent with the observation, and it will then give the agent the reward. And the goal of the agent is to train itself so that the reward is maximized. So in our case, the observation is this video clip that we receive from the camera, right? The action is the command we send to the beam splitters and lenses. And the reward, well, the reward actually naively, one would say, let's make the reward the visibility, right? The better the visibility, the better the agent performs. But we do something trickier. We, those of you who know optics, experimental optics, they know that the alignment has to be really good. That means that like a 95% visibility and 98% visibility is a big difference. And therefore we add this term here, logarithm of 1 minus v, which introduces this difference, motivates the agent to be thorough, right? And then we also add some penalty when the agent does something really stupid, like, moves the beam so much that it gets out of the view field. Of course, then you cannot do anything. You have to stop the process. Then the penalty is significant. So that's the reward structure. And well, I will stop. I will skip the computer science about training, right? That's the typical interference fringes that we see. One point that I should make is that well, the training is done in simulation. That's something I should really mention in the beginning of the talk. Remember, I told you that the only sort of frontier in machine learning that is not conquered yet is our everyday world, that is robotics. Why it is more difficult to train a robot than to train a chess player? The answer is that to train a chess player, to recognize a cat and a dog, or to train anything, you need a training set. But if the environment is already well modeled inside the computer, then you have the entire training set inside the computer already, right? So you can go through elements of the training set at the rate of 1 millisecond or 1 microsecond. But if you have a robot, then every action of a robot takes, a significant fraction of a second, right? So you acquire training set at a very slow rate, a much slower rate than the usual, in case of usual machine learning. And that's why it's so much more difficult to train a robot than to train a machine in a computer modeled environment. And there's a huge, field again, how to train robots in such cases, in such situations. It is rapidly developing, but what we do here is something simple. We just train on simulated data, right? We simulate the entire interferometer and train it. The problem is that the simulated data look like this. The real experimental data look like this. How do we deal with it? We deal with it in a standard way that's, again, common in robotics, called domain randomizations. That means we artificially introduce noise. We vary the beam radius, we vary the brightness, we introduce white noise to each pixel, and blah, 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 right? And then the interferometer, the agent trained with all these noises, then actually performs reasonably well in the lab. And here you can see how it performs in the lab. So as the alignment proceeds, you can see that gets aligned better and better. So now it's more or less aligned. And here's a comparison with a human expert. Now, it's an old paper in which we just change the mirrors and not lenses, but one can sort of so here blue is the agent and red is a human expert. A scientist who has aligned interferometers many times know what they're doing. And actually, well, you can see that the agent performs much better, but you can also kind of see the structure, and the structure is well explainable. So at first, the agent gets the first place at first, right? When in the alignment, in the beginning of the alignment, the agent gets ahead. Why it gets ahead? Because it's been trained on exactly that interferometer. It knows exactly what to do. It knows exactly which knob to turn. The human will need to turn knobs a little bit just to kind of get used to it, right? So it's a slowdown, but then once a human gets used to it, then it will move faster to the point of approximate alignment, right? And then it will slowly achieve thorough alignment by turning knobs a little bit. The agent, on the other hand, knows exactly what they're doing, knows what it's doing, knows what action will lead to which result. So it just steadily achieves better and better performance. And here's a final slide that kind of, I want to brag about something about the intelligence of our agents. And let me start with an example, unrelated example, seemingly unrelated example. Suppose you want to climb a hill, right? But you are allowed to only move in certain directions, like shown in this picture. And you're only allowed to take steps of certain lengths, like this and like this, right? Now, if you're greedy agent, then you would take steps like this. You would take a lot of steps to get to the top. If you're intelligent, then you would do something like this. You would take longer steps, right? But to get to the top much faster. But that means that at some point, you have to go down, right? So you achieved a certain height, and then you have to go down all the way to the bottom so that you can make it to the top in the next step. And basically, this slide here shows that our agent is indeed intelligent and not greedy. So you can see that here at point number 24, it's reasonably well aligned, right? But it takes, but to align it better, the agent will significantly misalign the interferometer, and then to point 25, then point 26, get back to the much better alignment point. So it's something that in optical physics is called walking the beam, and that's something that we show to our students, right? When we train them with optical setups, we teach them that to get better performance, you can walk the beam. Teach them that, and the agent has taught itself this trick. That's the second part of the talk. Again, I'm happy to answer questions.
Actually, about your last slide, about your this last comment, right? What makes this computer system, yeah, to go this to make this step? You think in your
practice, and practice. We train it, and a part of the reward is how long it takes, right? The longer it takes, the less the reward.
Okay, I had some question. Did you have during this work? Did you get some unexpected result, which was strange for you? Just for example, one of our students, he do the same, but in field of photo emission experiments, just to teach to recognize spectra. And my impression was that he include expectations that if he includes some additional relation, physical Kramers-Kronig relation in that sense, that system will be better, will work better. But it seems not the case in your situation, or for example, some kind of noise, some kind of noise, which noise you should add. Do you have some unexpected?
Well, we train with a lot of noise, right? So as discussed, right? We train with a lot of where is it? Here we train with a lot of artificial noises, and that's what allows the agent.
There's different kinds of noises, right?
That's right. That's right.
It's not just okay.
Yeah.
And some artifacts. Did you introduce some nonlinearity or just?
Nonlinearity is not relevant. You know, it's just a camera and two beams.
Special nonlinearity, some kind of.
Yeah, it's also not
aberrations like.
Aberrations we didn't. No.
So it works fine.
It works, yeah. I mean, of course, we kept introducing new things until it started working.
Yeah. Just with this spectral analysis, we have the same idea of that it should be trained on a number of simulated data and then applied to experiment.
Right. Yeah. I'm happy to discuss and connect you to the people who actually did the experiment. They have a lot of experience in reinforcement learning, so
okay.
happy to help. Okay, third part.
Maybe more questions here at this point.
Oh yeah, yes, please.
Okay, seems no question. Okay.
Right. So third half is again more. It's finally something that has to do with proper quantum optics. Super resolution. You know that all modern optical devices, all imaging devices, suffer from resolution limit associated with diffraction on the objective lens. Right. That's why a microscope cannot go beyond like a wavelength or half of a wavelength. Right. So if your object is a point, then your image will be a blur of the point spread function. Yeah, so if the sources are too close to each other, then the point spread functions will coalesce, and you won't be able to distinguish them. You won't be able to measure the distance between them. Now, there has been since the invention of microscopes, there's been a quest to overcome the resolution limit. People came up with two main scenarios. One scenario is near field microscopy, in which you have some kind of probe that scans your sample, and then everything occurs in a near field. Right, you touch the sample, there is no objective lens and hence no diffraction. That works very nicely. Another approach is via nonlinear optics. Basically, by means of nonlinear effects, you activate emitters, individual emitters in your sample. This has to be a specific biological sample, but you can activate your emitters one by one. And then you can achieve higher resolution, because to localize a single emitter is much easier than to distinguish, say, a pair of emitters with coalescing point spread function. But, because this is all nice, but both these approaches involve some kind of touching the object, some kind of active interaction with the object. And the question, the million-dollar question, is, can we really avoid this? Can we come up with a passive imaging device that does not touch, does not actively interact with the object in any way, but instead just uses the light arriving from the object in a wiser manner? And of course, this would be a huge thing. It could change. It would be useful in microscopy, because there are some objects that are delicate, that have no nonlinear properties. But also there is astronomy, where there is like no possibility at all to have any active interaction with your system, right? So a device, if we do manage to develop something like this, it would really change the face of the entire imaging technology. But of course, this appears to be a problem, because the diffraction limit is based on very solid science. It was developed 150 years ago, and nobody really questioned it until about 5 years ago. A young scientist by the name Man-Kei Tsang said, yes, we can overcome the diffraction limit, but we have to reject our traditional measurement approach. You see, what's a traditional measurement approach? Traditional imaging means measuring the intensity of your image as a distribution of intensity in the image plane. Instead, what you could do instead is you could do a fundamentally different measurement. You could look at correlation of field amplitudes at different positions. Yeah, so instead of intensities in the individual positions, you can measure correlations at different positions. This is, of course, a very superficial description. What is done, in fact, is that you take your image and you decompose it into a certain transverse basis, for example, the Hermite-Gaussian basis, right? And then you measure the intensity in each basis element, right, in each of the modes. You decompose the image into Hermite-Gaussian basis, and you measure the intensity in each mode. And here is an illustration to the intuition why it works. Suppose you have, for example, a star, and it's sitting on the optical axis of your telescope, right? And here in the imaging plane, you put in some kind of filter that only transmits Hermite-Gaussian 0-1 mode. Now, if you remember, that's an asymmetric mode, and the source is symmetric. The source is on the axis, so a point object will not produce any light on this photon detector. But if you displace your star, then of course light will be present. And moreover, if you have two stars like this, then you'll still have some light in your photon detector, even if these two stars are within the diffraction limit. So even if you cannot distinguish them by traditional means, you can still distinguish them and measure distance between them by this technique of filtering of the Hermite-Gaussian 0-1. And that's basically what Man-Kei Tsang has proposed. He analyzed it using Fisher information. Basically, well, this again a kind of cartoonish intuition. You see, like here's a picture of one emitter, here's a picture of two emitters. You can see from this picture we cannot really tell it's two emitters and cannot measure the distance between them. On the other hand, if you have this new method, well, we have to distinguish between no light and some light. And distinguishing between no light and some light is much easier, even in the mathematical sense, is much easier than distinguishing between a picture and a slightly different picture. That's the difference. So that's the ideology. And well, what we've done, what our contribution to this was, is that we've extended, so Man-Kei has done this distinguishing between point sources, but what we've contributed is we said we can actually extend it to full imaging, so not just not just 2-point sources, not just measuring some parameters of your object, but really reconstructing the image. And the way we can reconstruct is simply, well, measure the amplitude of Hermite-Gaussian mode, not just Hermite-Gaussian mode 0, 1, but multiple Hermite-Gaussian modes. And if you calculate the intensity, or in this case, the amplitude in each in the mnth Hermite-Gaussian mode, you will see that this amplitude is actually the mnth moment of your source field distribution. And obviously, if you measure all the modes, you'll get all the modes of all the moments of your distribution. As we know from statistics, if we know all the moments of the distribution, we can reconstruct the object. So I will skip a lot, but here this slide shows the resolution enhancement one can get with the number of Hermite-Gaussian modes one uses, right? So if one has, for example, 20 Hermite-Gaussian modes, the basis of 20 Hermite-Gaussian modes, one can enhance the resolution by a factor of about 3. Now, of course, all of that requires you to sort, to have some kind of experimental technique of decomposing your light into Hermite-Gaussian modes. In principle, such techniques exist, or they're being developed. There's even a startup that specializes on this, but it's really difficult to do in practice. So the trick that we came up with is heterodyne detection. That is, a heterodyne detector has the property of detecting light only in the mode of the local oscillator. That is, that if you prepare your local oscillator in the Hermite-Gaussian mode of interest, then the signal that you get, the photocurrent that you get in the output will be proportional to the amplitude in that mode of interest. And that's exactly what we are doing. So here's the experiment. Here's the experiment. We take a laser. We print an object in a digital micromirror device. The whole thing is not really microscopic. So far, it's quite macroscopic. It's the object is a few millimeters, and we artificially put an iris here to restrict our aperture, and therefore restrict our aperture, and therefore impose the resolution limit. So this is the object path, right? So the light from the object after passing through the iris is imaged by this objective lens. And here's the local oscillator path. So the spatial light modulator produces the local oscillator in the Hermite-Gaussian mode of interest. And the two are overlapped on a beam splitter and then detected by this heterodyne detector. And here's the setting. Here's the object, the logo of University of Oxford. We divide it into little squares. And well, here you can see an individual square, and here you can see the point spread function. You can see that the point spread function is, well, with a point spread function like this, you cannot really distinguish individual letters. Now, one point I should make before I show you the results is that, well, remember we have this equation. We had this equation here that the amplitude in each Hermite-Gaussian mode is the mnth moment of the field distribution. This, unfortunately, works only in theory. In practice, you have lots of problems. You have aberrations, you have noise, you have imperfect Hermite-Gaussian modes in your local oscillator, you have your aperture is not Gaussian, and so on. So to address all of this, well, you have to use a neural network, right? So the way we do it is we have a training set. So we produce a training set. For each training set, we measure our photocurrents with a heterodyne detector, and that gives us the output, right? So for each element of the training set, we have the input. We have the input, which is the photocurrents, and we have the output, which is the reconstructed object. And then we train it with a few tens of thousands of elements, and then we show it the university logo, and the reconstruction looks like this. So here you can see the original object, the university logo. Here you can see the direct image, and you can see that the resolution is quite poor. And here you can see the object reconstructed by our method, and the visibility, the resolution is much better. The resolution can be quantified by looking at pairs of lines. You have various pairs of lines, and you can see that direct imaging can only distinguish pairs of lines that are 110 pixels apart, whereas our method can distinguish pairs of lines that are 56 pixels apart. So the resolution by our method is enhanced by about a factor of 2. This works both in the coherent and incoherent regime, and there are some open questions, but it's time for me to conclude. I'll do that. So you see, the technique works in principle, right? So we've achieved our main goal, that is, we've demonstrated that by passive observation in the far field and using only linear optics, we can still achieve significant enhancement of the resolution as compared to diffraction limit, right? And we've done it for coherent and incoherent illumination, and we validated it through quantum figures of merit, something that I have no time to talk about, but still a lot remains to be done before it can become a universal microscopy technique. So 2 things mainly. One is that we need to extend it to proper microscopic objects, right? So right now, as I told you, it was a toy setup with a macroscopic object, but can we do it with truly microscopic objects? In particular, how would we construct a training set in the case of a proper microscopic object? That's question number 1. Question number 2 is related to that. You see, heterodyning, as I told you, it's technically more convenient, but it also has a problem. The problem is that the spectral range accepted by a heterodyne detector is limited by its electronic bandwidth, which is, no more than a gigahertz. On the other hand, fluorescent samples with which regular biological microscopy deals has a much broader bandwidth of tens of nanometers. So it means that we can no longer use a heterodyne detector. Instead, we must use a proper mode sorter. So we must develop a mode sorter that would, take the input light and send the light contained in different transverse modes into spatially separable directions. So that, and well, Andre and I have submitted a proposal, actually a couple of proposals, which hopefully allow us to conduct this experiment. Thank you for listening.
Thank you, Alex. Please, questions. Your last part just remind me one of our lectures when I was student like to repeat that our eyes refuse to solve the convolution problem. And Mike, I would reformulate it in the question, why do you think during evolution our eyes and mind could not do the same? Could not resolve, could not make this operation, or it does?
Very good question. Indeed, right? So it would appear that by deconvolution, one can achieve perfect resolution. But as you know, deconvolution is extremely, extremely sensitive to noise. Right? So it's a technical problem, but because light is quantum, because light consists of photons, we have shot noise, right? So in fact, when we do all these quantum criteria, when we calculate quantum limits to resolution, it's always the resolution per photon, because the more photons you have, the better you can do the deconvolution. So it's all included, but because the number of photons is limited, you cannot really deconvolve. Your microphone is off.
No, my microphone's here.
Yeah, okay. Alex, may I ask a question?
Please.
Yeah, I would like. So, Alex, could you please comment a little bit about, in more details about this mode sorter? how it works, special modes order.
It's simply a diffractive device, right? So it can be a spatial light modulator, but can also be a faceplate. So some kind of device on which different modes diffract differently. So one can show that using a faceplate, one can implement any arbitrary unitary transformation of spatial structure of light. Spatial structure is a vector. One can do any arbitrary unitary transformation of this vector. In particular, you can send different transverse modes into different spatial directions.
But how good is this unitary transformation? I need, for example, as a theoretician, I told you, Alex, I need such a unitary matrix. Yeah. So can you guarantee that you will get exactly this one, or with some plus minus error?
Well, of course, errors are present, right? And that's why existing mode sorters are not perfect. One needs higher, the higher the resolution, of course, the better, the higher the bit resolution and the higher the pixel resolution, the better precision of your transformation you can achieve. And plus, theoretically, well, I mean, of course, it's also a complex theoretical task of how to produce the transformation, how to implement the transformation by a faceplate, but in principle, there exist methods to resolve it.
Okay, thank you.
Welcome.
So, do we have other questions?
There is a question in the chat, I think.
Yes, in chat something, yes. In chat I can write, is it possible, so it's from Sergei Balchevsky, question, is it possible to see somewhere this presentation a bit later, proper, I believe, yes, it's possible, yeah? Alexander.
So I think it will be placed on YouTube.
Yeah, on YouTube.
We will put it on YouTube and reference, of course, here.
There is a YouTube, so just go to YouTube channel of the Kyiv Academic University and playlist quantum seminars, and you will see it there. Okay.
Okay. Well, thank you very much for listening.
Yes, thank you very much for your very interesting talk. Yeah, maybe some people wrote me that they were not able to join, unfortunately, due to some hard obstacles, but okay, maybe hopefully they will be able to see this presentation later on YouTube. Now, technically, we have such a possibility. So, thank you very much again. So let's thank our speaker again, Alex, and hopefully this is not the last talk that we have from you. And hopefully also for a productive collaboration. Thank you very much.
Me too. Thank you. Bye.
Thank you, Alex. Just the last question. I just waited.
Oh, but no.
That about when you the second part of your talk, right? About how you make it by robots. How it is realized? Did you realize that robots moves the motors? And
oh yeah,
how many motors and is it how
okay.
it was realized
here
in
this video? Motorized mirror mount.
Mm-hmm.
Yeah.
And how many mirrors?
Well, 2 mirrors and 2 lenses.
Uh-huh. Because from your picture, I thought that it was hundreds of mirrors. And
no, we're not that far yet.
Uh-huh.
We're not that far yet. We can just do a single interferometer for now.
Okay, then thank you very much.
Right, thank you.
So thank you very much. We can close our seminar.
Yeah. Bye, everyone.
So bye. Thank you.
Thank you.